Hello everyone. Today we will be discussing about some concept related to the behavior of real gases. Today we will discuss van der Waals equation of state, critical properties of gases and case rule for gases mixture. These concepts are widely used in chemical engineering because real gases do not always behave according to the ideal gas, especially at high pressure and low temperature. So let's begin with the van der Waals equation. The ideal gas law assumes that gas molecules have no volume and no intermolecular forces. However, in reality, gas molecules occupy space and attract each other. Therefore, real gases show deviation from ideal behavior. To account for this deviation, van der Waals proposed an equation of state for real gases. So here is the equation: P plus A by V square into V minus B equal to RT. In this equation, P is the pressure, V is the molar volume, T is temperature, R is universal gas constant, and A and B are the van der Waals constant. This constant A corrects for intermolecular attractive force. Because molecules attract each other and actual pressure is lower than predicted by the ideal gas law. Therefore, a pressure correction term A by V square is added. The constant B corrects for the finite size of gas molecules. Since molecules occupy volume, the free volume available for movement is less than the total volume. Therefore, the volume correction here V minus B is used. The values of A and B depends on the nature of the gas and can be determined experimentally. This constant can also be related to the critical properties of the gas using the equation shown on the slide. So here is the equation which are highlighted. Thus, the van der Waals equation provides a more accurate description of the pressure, volume, temperature behavior of real gases than the ideal gas law. Now let us understand the critical properties used in this calculation. Okay, so here is A equal to 27 R square Tc square divided by 64 Pc and B equal to R Tc divided by 8 Pc. So here Tc is critical temperature and Pc is critical pressure. So let us understand this property. So first, the critical temperature. It is denoted by Tc and is the maximum temperature at which a gas can be liquefied by applying pressure. If the temperature here, if the temperature is above the critical temperature, no amount of pressure can convert the gas into a liquid. This is important note. Here is the note. Now, critical pressure. It is represented by Pc and it is the pressure required to liquefy a gas when it is at the critical temperature. So it is a basically saturation pressure corresponding to the critical temperature. Now, critical volume. It is the volume which is occupied by a gas at the critical temperature and critical pressure. These critical properties are very important because they characterize the behavior of the substance near the phase transition region. An important point to remember is that the above critical temperature, here is the note, above critical temperature a gas cannot be liquefied regardless of the pressure applied. Critical properties are extensively used in thermodynamic calculations, equation of state models and process designs. Now let us see how these concepts are applied when we talk about the gas mixture. So here is the case rule. dealing with the gas mixture, determining the exact critical properties becomes more complicated. To simplify, this case rule is used to estimate the pseudo-critical property of the gas mixture. Now, consider a binary gas mixture containing component A and B. So X1 and X2 are the mole fraction of A and B. Tc1 and Tc, so Tc2 are the critical temperature of A and B. Pc1 and Pc2 are the critical pressure of the A and B. So, how we determine Tc, critical temperature of gas mixture? So here is the formula: Tc equal to x1 into Tc1 plus x2 into Tc2. Similarly, we can determine the critical pressure: Pc equal to x1 into Pc1 plus x2 into Pc2. In other words, the pseudo-critical properties are obtained as a mole fraction weighted average of the critical properties of the individual component. Now, these pseudo-critical values are widely used in compressibility factor calculation and in predicting the thermodynamic behavior of the gas mixture. Case rule provides a simple and practical method for estimating mixture properties when detailed calculations are not required. So, understanding this concept is essential for the analyzing and designing many chemical engineering processes involving gases or gas mixture. Thank you.